Good evening, everyone. This is a stream about mitigating hash collisions. And welcome to the stream. And hopefully, it works better than yesterday. And let's see if it connects. Does it work? I don't see myself appearing on the screen. Yes. Okay. It's a bit slow. Okay. It's a bit slow. Okay, so if you're not familiar, I'm doing live streams on file format oriented streams, from very basic topics to weird files. And recently, I started uh, talking about hash collisions exploitation. So I'm not a cryptographer. I'm not able to design new hash collisions, but I had at least 10 years or a bit more than 10 years of collaboration with different cryptographers regarding hash collision techniques. And especially because it's one of the field where knowing file formats really makes the attacks much stronger. And for example, when I joined Google almost 10 years ago, very shortly after joining Google, I was put in contact with Mark Stevens, and the idea was we're gonna compute a SHA1 collision, and let's do a PDF. What can we do with a colliding PDF and a SHA1 collision that was not computed yet? So the direct impact of having a hash collision is that, for example, as soon as the SHA1 collision of Shattered were released publicly, the two existing files with different content, the SHA1 and the same SHA1, this failed all Apache Subversion servers everywhere. So that caused a major trouble and it required an update. And yeah, that was there was no fix except I mean there was no workaround because it would enter an infinite loop or something. And then this just required an update. So even without any cryptographic consequence of like having a certificate that is signed for everything or whatever, then even having a SHA1 files with the same collision with the same hash can lead to troubles. And nowadays, for example, Gmail is using a tool that we'll mention later by Mark Stevens to prevent attaching. So you might want to avoid people for people to attach hash colliding files. So VirusTotal has a tag for hash collisions, okay? But this tag is so, for example, in the case of the Nostradamus PDFs that Mark Stevens created many years ago. Sorry, of course, it's always more than 10 years. 10 PDFs having the same MD5 and with dead in the middle. I don't know if it's so, and all these PDFs being about um, predicting who's the next US president would be. That was in 2008. And basically, all these files have the same hash, it's a chain of MD5 collisions, and they have the same MD5. And in this case, because there are two contents that are different, and they have the same one identical hash, then VirusTotal um, is able to put a hash collision tag, but it's only in this case. And if we take the extreme case of the flame, also known as Skywiper, the malware that was using unknown at this time MD5 collision to create to basically impersonate a Windows Update server, so that infected computers would automatically download malicious updates silently. That was a exceptional and a unique case of a very new hash collision, and we only have one file. We only have the malicious file for that. So even though it's possible to detect that there is a hash collision in this file, VirusTotal, for example, is not able to buy because it doesn't have the other certificate with the same MD5. Okay, no questions. So So now a question I have repeatedly in the past when I explained how hash collision were possible thanks to file formats and so on. So if you're curious about that, uh, check the stream number 18. And if you're not I'm gonna say, and yeah, people were really surprised that it's possible because of various tricks. And for that, this is actually the slides of this part of the slide deck that for this stream. And let's see at what is making different kinds of hash collision structures. So you have in the case of a reusable identical prefix, you have a prefix that is most likely the header of the file, and this is identical on the two files. Then there is always some requirement of an, how do you say, of padding until 64 bytes. And then would be some collision blocks. These collision blocks have a very high entropy and are also vast majority uh, a multiple of 64 bytes, so 14 hex. And then it would be whatever comes after collision block should be identical on both sides, so that the file length is identical, and that makes the file very easy to detect, to notice that there is something wrong in the structure. So for example, let's see, do we have a fast call with prefix, unicall? So if we have fast call with prefix, this is, you see that there is identical content at the very beginning of the file. Then there is some padding to a multiple of 14 hex. Then there are blocks, one or two or more blocks with very high entropy, with a lot of randomness, and with only very tiny differences in the middle. And if you want to put some data after it for the collision to be identical, for the hash to be identical, then the suffix has to be identical to both sides, which is all this part here. It has to be identical on both sides, even though it's parsed differently depending on each side of which file of the pair you are parsing. Okay, so again, a very strong noticeable structure. So let's take some PNGs and PNG, and this is the pair. And again, you have a header that is okay, that is something, but again, there will be some alignment to a multiple of 40. Then there would be two blocks. We can see them here. There will be two blocks. In this case, it's two blocks. Most of the time, it's two blocks for IPCs and something like 7-9 blocks for CPC, for chosen prefix collision. There will be more blocks, less blocks, but there's required more computation. Of course, there can be only one block if possible, but that's a very extreme case. That is the case of a single block hash collision, but it's not that. It's definitely not. It's technically possible, and this is here CPC. So, and again with one block. Can I do it? Yes, exactly. You can see that there's only one block with high entropy after arbitrary content, but this is a very exceptional case of computation. Okay, so we have the two blocks of collision. Then there will be whatever is the prefix, the suffix, and the suffix will be identical to both sides. So at the end of the very end of the file, you need to have exactly the same length. Here, I'm showing swapping between the two different files, and you see that the end is strictly identical, and the length, of course, is identical too. So this is a very strong, noticeable, but definitely not so easy to do at scale, right? I mean, you can observe it manually, but it's not very easy. And in the case of the flame prefix, so the unique one, again, you will have something that indeed looks like a typical certificate structure, and then after this point, at a rounding of again 40, you will have suddenly large blocks with high entropy, which is kind of a giveaway. But again, if you don't have the other file, it's not that trivial to say. You on the other hand, if you notice that there is a command that looks, I mean, it's in this case it was a chosen prefix, right? So it's definitely not trivial. So no questions. Let's go further. So in the other case for chosen prefix is that you can have two different prefixes that have nothing to have in common. They can be entirely different in length or whatever in content, but they will be padded to the same length. So the longest, they will be all padded to the longest of the two. Then there is again an alignment to 64 bytes, 14 hex, with some data just before used, sacrificed for a, a specific part of the computation. And then again, some number of blocks. And for example, in the case of two files saying yes and no, you see that there is the prefix here that are different, but they could have very different length, right? Again, then there is some padding to almost 40, except that a few bytes are sacrificed just before the end of the prefix. You see that there is a difference between the two files, and then you have typically 7 to 9 blocks of 40 in hex with high entropy again, and with tiny differences in the middle. So this is a yes/no chosen prefix computation with for MD5. Okay, and again, 7-9 blocks is something standard on a normal computer, on a home computer. You need a lot more power to compute a single block collision like Mark Stevens did. And reusable CPC is actually even the same. It's just that there are tricks, but in terms of structure, definitely again for reusable hashes, it's very easy. It's easier to identify a hash collision because you have two sets of payload simultaneously in the file. So even if for the case of a reusable CPC, you will see the differences between the two files. So for example, if I take two P files with so this is a reusable CPC. This is a reusable CPC for a Windows executable, and you have the header. And the header, if you notice that the suffix, the prefix, sorry, the header is a prefix, and the only difference is where the pointer to the P address is. So this part here, and the rest is the hash collision. Okay. Oh yeah, yeah. Also, I made some effect regarding to ASCII art, and Mark and Ange are swapped. Okay, but then CPC how do you say collision blocks, and then after that you will see that there will be two P headers, which is extremely suspicious. So basically, whenever you have a reusable collision, you will see twice. I mean, you will see something like twice the structure, which is extremely suspicious. But again, it requires some scrutiny, mathematical or parsing scrutiny. I mean, we will see that both are possible. But yeah, it's visible, but it's not something you usually scan for. Usually, but just the fact that one of the P sorry, why didn't it jump? Oh, not sorry. The one of the P header is very far in the file, which is very unusual, you know. So already this one at 2C0 is pretty far for a P header, but this one at 480, That's very unusual. So probably it's going to trigger some heuristics already. Okay, so the file structure overall of these collisions is weird. Uh, and in the case of a reusable collision, super easy. But again, if you want it to be stay undetected, definitely only use the CPC like the flame one, so that you don't reveal the other payload, and it's harder to check, even though it's possible, and we will see that it's mathematically possible. So the question I got often is that how come people can easily abuse files by crafting? So basically, you will use something like a parasite here for the padding, then you will abuse a length for the collision to jump at different distance, and then you will hide one of the payload with another command. So basically, you end up chaining three commands or metadata structures in the file, and usually you would probably only have one such structure maybe in the file, but here you chain several of them. And people ask me, how is it possible to store such data in a file that doesn't belong to the data? But that's actually what metadata is about. And metadata is actually super important. And let's go back in time for the origins of the mp3 file, before it's what it is today, even though the data technique is almost the same. So basically, in 94, the MP3 file started as officially the layer 3 files. The extension was .l3, and they were just raw bit streams, no header, and just sequence of frames. So that's 50 milliseconds of silence encoded with the original L3 hank. And as you see, there is no visible pattern. There is no trick with byte distribution. And it's actually just 3 frames. And you just have a small frame header in between with the FFB, which is the frame marker. And this is the first frame, and so on. You get the idea. So basically, that's 3 frames. So the first thing is that this was not a great idea, because it makes very difficult to identify such files, and actually you end up identifying them by heuristics. And if the file is too small, basically what you do is that you see there is an FFFB something, you get the parameters, and you see, is there another one further, and is there another one, and after enough frames, yes, maybe it's a mp3 files. But in practice, the most software could just they could just be wrong. And the thing is, JPEG also use these FF markers. So basically, this is a famous bug of, I should see a muscular girl in the JPEG file, and I hear musical industrial music instead. And this was actually abused the other way around, where people were putting MP3 inside a JPEG, and you could play directly the JPEG inside a music player to hide copyrighted songs or whatever. So this format was a clever compression idea, but standard file format, and people wanted to store obviously the names of the song or the artist and whatever. And it's actually in the past, long before, on older computers, I mean long before, 10 years before, let's say, people were actually this is mod file, this is a Amiga music tracker music file. And typically these formats at the end didn't have a magic, because you wouldn't have so many files. It was on computers that didn't have hard disks typically. And basically, on the other hand, identifying your file was very important. So it was very common back then that files start with files start with metadata, so that you can identify your file as soon as possible. The file type was not so important, but here you see that the file, the music already starts by the name of the work. So this is what people wanted for the original MP3, and someone just created a hack, because this format was always the same with no possibilities of header and so on. Then someone decided to add a footer, which is a way to add some metadata, but still not change the beginning of the song and everything. And it's only some time after that, and there were more footers that were created and so on. And it's only some time after that eventually came a new standard, the ID3 header that is used nowadays. But an MP3 file, a modern MP3 file, is still an ID3 with the same kind of MP3 raw data. And you see that there are other flavors of file formats which could use exactly strictly the same structure. Okay. So basically, storing metadata is something we want. Another format that will start with metadata is the tar archive, where again, this one even slower than floppies, most likely. The tape archive format starts directly with the file name. So, oh, that's funny. There is a big mistake between this and this. Okay, that's probably why I didn't make this thing public. So you see that metadata is definitely something that is normal in a new file format, and typically when formats without metadata, without abilities to store metadata, end up being hacked like MP3 or forked, like adapted to a new format, but won't stay as is. A more recent format of that is the quite okay image format that has the very tiny header and no room for any metadata, which I think makes it a bad file format, a clever compression format, but not a good file format. Okay, so the first abuse is by metadata, but as we saw, the second abuse, the other kind of abuse, is via what could be appended data. So basically, you took a yes and a no, and you add collision blocks, and it's how can I say? And then this is ignored by the rest of the file. So basically, it's appended data. And there are formats that don't like appended data. So for example, BPG, the Fabrice Bellard, the QEMU guy, QEMU author, start with a small header and then the pure data. And if there is something that is not data at the end, then and the picture data length might be unspecified. When it's 0, then it's until the end of file. And in this case, if there is some extra data, even if the file is complete, let's say in width and height, then the file is rejected. DCOM. DCOM is the medical image format that you may not be very familiar with. It's a bit like TIFF in terms of structure. It just starts with some ignore space, but then there is a signature out of set 80 in hex. And then there is a sequence of like TIFF, tag, length, value, and so on. And then there is data, which is in itself in another of these structures. And typically, if there is any data on top more than that, the DCOM file is rejected. So here it's more like they decide to reject the file. It's not that the format is preventing appended data, but so again, appended data is a very standard thing in formats. Some formats may want to say, hey, I finished my file. Is there something else? If not, reject the file. And typically the case is like, oh, my file is complete. Whatever, I stop parsing here and I ignore the rest. So basically, there could be collision blocks. And there is also the typical exception that, for example, if you take a PNG and you remove the image end marker, then the PNG will still be valid because there is all the data needed to render the file. And there's no end marker. Yeah, well, if there's nothing else, it's probably good enough to render the file anyway. So basically, many parsers will to avoid being picky and actually working faster. Oh, do I have all the data to parse the file? Then there is no need to parse further. And if there would be collision blocks there, then let's ignore it. So basically, having tolerating appended data is a very common thing, and it kind of makes sense. And a format that took a different approach is the XZ format, where you have a stream header, block header, and so on and so on, and then you have a stream footer. And for the file to be valid, you need to have this stream footer, which contains a CRC, which contains a signature. So basically, the file requires a footer, so you cannot append something and keep the file valid. You could need to check this file. The thing is here that is missing is that typically the thing is when you want to parse such files, and you would like to go very quickly at the end. So either you can hop between structures like PNG, but when it's unclear, when you cannot jump quickly, then it might be very time consuming to check for the whole file. We'll see that it could be useful because, for example, in all the other formats, if you could jump quickly at the end and automatically clean the appended data, that would prevent hash collisions. Okay, so basically, yes, you would like to. Would it be possible to clean specific structure and that way prevent hash collision exploitation? It requires checking every block, and for some format, it's very picky. It's very difficult, and so again, visually, it might be easy to do it for one file, but for all the file formats and so on, yeah, it might be very tricky. There is no such tool as far as I know. And again, a command with a weird length, and for each for a given format, let's take, for example, PNG header. So again, you have the PNG signature, then you have a block, alignment chunk that is used here. Okay, it contains text, who cares? And suddenly you have this block that is aligned to 40, that has only high entropy. Very, very suspicious, perfectly aligned. Yeah, so that's because the PNG structure is very easy to navigate, quickly hop through all the structures of the file. You can first remove all these blocks. Even better is that there is no absolute offset in PNG. So basically, if you would take this file and remove this collision block, immediately the file would be still valid. While if you take some, for example, an MP4 files have this what was it called? They have a structure that is absolute offset in the file, which basically makes it where was it? Is it in that file? Some file may not have it. I'm trying to remember. Yeah, exactly. That's probably this one. So it's probably STCO. If I recall, this is the name of a MP4 atom, and this means something like stream check offsets or whatever, and these are absolute offsets. So basically, if you would remove, for example, these three chunks, so the length is first. So if you would remove these three chunks, then the file would be invalid. So making it harder to clean up because of this absolute offset. You would need to readjust the offsets of this STCO ST64. There are two versions, 32-bit and 64-bit, if I recall correctly. So basically, but Mitra can do that, right? When making polyglots, Mitra can actually, it's not very difficult, but it makes things just a bit harder so that you cannot easily trim potential abuse collision blocks. And although it will be a bit more time consuming to just hop until the end of the structure, but again, in the case of MP4, that's still okay. So basically, you might want to, if you were very suspicious, if you wanted to make sure, you could indeed regenerate the files, removing all the command that could host parasites and appended data. But some formats make it super easy, and some formats will make it much harder, if not very difficult. Now, detecting hash collisions. So the very first easy, stupid way to detect hash collisions, if you saw they have some given patterns, and actually, in the case, for example, of fastcall, you can easily, the offsets of differences are always around the same spots. So basically, what you can do is just say, hey, oh no, this is not the call. So this is one of my source that is on my repository. So on my core collisions hashcoin scripts, and it's in collision, the script, and it's just, hey, let's try one side, or let's try the other. And if the MD5 is the same, then it was a collision block. That's brutal, but that works. And that works for actually even shattered. And you can also flip the collision around if you only have one file. And as I mentioned, when Mark Stevens gave me first of the first time the SHA1 colliding prefix, he just gave me one because he knew that it was possible to generate the other side. So you can flip collisions, and in the case of non-chosen prefix collision, again, you have the header, right? It's just identical prefix. If it's chosen prefix, of course, you cannot guess the missing prefix. But you can flip collisions easily, and that's a very easy way to detect that, even though it's a bit weird, but it works. And also, it's enabling you to flip the collision without. I mean, you can even do it automatically. And yeah, I wrote some source for that. Okay. But thankfully, we have better solutions, and the best solution is Mark Stevens' Detectcoll. So Detectcoll is on his hashclash repository, but it's on the collision detection block branch. And where is it? It's in source detections or something, if I recall correctly. Can you load collision detection? Exactly, it's pretty short. You will see that. So this is math magic. And this detects all the non-collisions, even for flame, shattered, shambles, and so on. One particular thing is that it requires some signatures, which, because at some point some of them were missing, so basically it could still fail to detect some stuff. Those are the signatures that I'm referring to. But basically, right now, I actually there's an example, and yeah, this is Detectcoll unsafe. Oh, okay. So we need to mention that. So Detectcoll has a bit of very technical output, but at least if it tells you something, it can even tell you that there's a that there is a collision in the flame certificate, which is definitely not a random property, right? You don't never get this by accident. And since this is a bit cryptic, I ended up generating a kind of post. So this tool is called Detectcoll, and as you see, it works on all the hash collision that exist. And I created a small log parser to just come up with some signatures that will match these cryptic names to something more understandable. And this is exactly what I would use myself, and you can run it yourself. So basically, it is possible to detect collisions. It takes some time. You need to parse just every block and do some computation on all of them. It is what's protecting, what is preventing many projects from attaching or whatever, sending hash colliding files. It's even working. I didn't mention that yet. That will be a future presentation, a future stream, but let's spoil a bit. The amazing text collision. So this is a text that is MD5 colliding. And as you see, it's not even the usual length. And so basically now you can have text-only collisions that, for example, this is with base 64, and you see that just one single, how does that work again? So just one single byte of difference, predictable like Unicode, but pure text. And yeah, this is pretty amazing. This is something that Mark Stevens came up with last year, and it was even used in a challenge. So these are two Python scripts, And as you can imagine, they will behave differently because of the sharp turning into a quote. And this was the string to import OS read the flag. So that was one of the available solution. I contributed to that challenge, and it was used a brand new. So this is a valid Python snippet, Python script, which is also MD5 colliding. And this is very good because now we can test the password entries. I mean, it's a bit long, but yeah, nowadays collisions with pure text are possible. And Detectcoll is also detecting um, Detectcoll is detecting collisions in these files. So basically, there is a tool that already exists that makes it possible to detect all hash collisions. Now there is a mechanism that Mark came up with, that there is a safe hash, because the problem is that, of course, it would give the same hash for two files that are identical. And then Mark came up with something that is safe hashes, which like it reprocesses it again to break the collision property. So it's able to tell different files apart, even though there is an actual collision. That's useful, but the thing is with safe hashes is that it prevents detecting uh, multiple collision in the file. While if you disable the safe hashes in a file that has a lot of collision, then it will be able to find all of them. So basically, safe hashes might be useful to distinguish two files that would be colliding, but still give you some output to distinguish them. But on the other hand, you could just compute MD5 and SHA1, and there is no such a thing as a file that are both MD5 and SHA1 colliding. So that could do the trick, right? And then safe hash will go on computing on the rest of the file, and that way keep more collisions, identify more collisions if they are found in the file, even though it's very rare. I mean, I proved, but yeah. So basically, that's the last technique. Did I close a tab too much? Oh no, here. Um, so again, the Mark Stevens Hashclash repository, but with the collision detection branch, and for a nicer output if you want. But again, I wouldn't have done that without Mark's help, feedback, and so on. Just a nice way to identify, to tell apart the different kinds of collision, which is very nice, right? Especially for me sorting all my files. I mean, for me or for you, right? If you want to, yeah, like you have everything you need if you want to detect at scales hash collisions, except that I mean, just be aware that it will take too much of computing, which is why VirusTotal cannot afford running this such a tool on all the samples of the set. You get the idea, right? It's pretty obvious. And it's not that hash collisions are a big thing anyway, but at least now you know everything I believe there is to know regarding detecting them. If you want, I mean, I would say that if you have some specific format and you want to make sure, just implement some cleaning up, or just check if they don't have some specific property or structure, like the high entropy collision blocks in commands. That's very unusual, except if it's compressed blocks, of course. So you get the idea. And now I believe you know everything on the topic. I see no questions. So I thank you for your attention. I thanks I thank Mark Stevens a lot for all his help through the project, and we're not done yet. Uh, I might do a new topic on a new presentation on text collision, which is still very impressive. So that's all these files are text are MD5 colliding. This one is called Lisp because as you can see, it's using a different alphabet. You can specify the alphabet for some ranges of the file, and that makes it possible to, for example, if you just want parentheses, why not? And Yeah, that's and the read flag too. Python script that is valid, and MD5 colliding, and very interesting enough to be a flag in Google CTF last year. Okay, so thanks a lot for your attention. And yes, see you next stream. Thanks for your attention. Bye bye.